This last section of Chapter 4 is a topic that's frequently covered in college algebra. But here we can use the ideas of calculus to explain why this topic is so common. We're going to be talking about exponential growth and decay. There are a number of situations that can be modeled by a function of the form y equals some constant e to another constant times t here being time, we use t instead of x here. That doesn't really change the idea of the model. If the k here is positive, then we're dealing with exponential growth. And our model looks something like that. The k here actually controls how quickly this grows. The c is actually related to where we start. For k negative, this is exponential decay. This time our model looks like something like this, where it starts at some point and then decreases to 0 over time. But why is this model so important? I mean, exponential growth covers things like compound interest, population growth, and a whole host of other things. Exponential decay covers a number of physical processes like radioactive decay and heat transfer. Why is that a common thing to have happen? Especially when it involves the exponential function. That seems like a weird thing to just suddenly come up. But it all boils down to something that we call a differential equation. A differential equation is something that relates a function to its derivatives. In this particular case, it's a very simple differential equation, saying that the derivative of the function y is some multiple of y itself. What this is saying is that the quantity y that changes over time changes in proportion to how much is already there. For instance, with compound interest, you could say our y here could be the amount of money in an account, and how much interest you earn is how much it changes. And that interest that you earn is a percentage of the current balance. If we try to solve this differential equation, which basically means we're looking for a function that satisfies the equation, we can look at something like the equation that the function I gave you before. This works because if I differentiate this function, the c is a constant, so it just stays there. We need to essentially use the chain rule here. We still have the derivative of the e to something power means that we still have an e to the something power, and we need to multiply by the derivative of the inside. Derivative of k times t is just k, because t is our variable here. It's our x in this case. And so our derivative of y is just y itself. This is just y as it was originally, but now times the k that we have in our formula up here. This means that this function is a solution to this differential equation. Now there is a question of whether there could be other solutions, but it turns out that all of them look like this. This is really the only solution. Though technically there are infinitely many solutions here because the c can be whatever we want. Speaking of c is frequently called the initial value, because it basically is what we get when we plug in 0. If we plug in 0 into this formula, get c times e to the, 0 times k is still 0, but then e to the 0 power is a 1. So we just get c. So we can actually incorporate that into our pictures here. We start at a y value of c. Now the k, that controls how quickly it either grows or decays, depending on which situation we're in. K is frequently referred to as the constant of proportionality. And the importance of this constant is that it is related to what the derivative is. It's controlling that rate of change. The rate of change is whatever you had times this k. Now, this is not really a differential equations class, so we're not going to go too far into this. We're just going to use the fact that we know this is a solution to solve various problems. Basically, look at some examples. Let's start with problem 23. This is a problem about population growth, specifically population of bacteria. A number of a certain type of bacteria increases continuously at a rate proportional to the number present. So you could say that we're dealing with the derivative of a y is equal to some constant times that y. That's all that they're saying here. The rate of increase is proportional to the amount present. We're told that there are 150 present at a given time. We're going to assume that that time is our time t equals 0. And then we're told that we also know that there's 450 after 5 hours. And then we're asked to solve a few questions about it. But the first thing we want to do is set up our model. Get rid of that. So the fact that we know that there are 150 present at the given time means that our c in this problem is going to be 150. We're going to assume that at time t equals 0, we have 150. So our model looks like y equals 150 e to the kt. We don't know what k is yet, though, and they didn't really tell us information that immediately gives us k. Instead, they gave us information about what this looks like at another time, and we're going to have to solve for k. So we'll use the fact that when t equals 5, the y should be 450. So 450 is equal to 150 times e to the 5t, or not t, 5k, because I'm replacing t with 5. And this is now an exponential equation that I need to solve to find out what my k value is. So remember, the first step of solving an exponential equation like this is to solve for the exponential itself. Solve for this e to the 5k. Basically, I get to divide both sides by 150. Which is kind of easy because the 450 actually is divisible by 150. Now that I have an exponential equals some number, I can turn this around and turn it into a logarithm problem. Basically, the fact that we have 3 outside means it's now going to be inside the logarithm. And this stuff that was inside the exponential is now outside the logarithm. So my k is just going to be ln of 3 divided by 5. And at this point, you can go ahead and just use a calculator. I'm going to write that as 0.2197. So our model for this problem is y is equal to 150 e to the 0.2197 t. Of course, that's not answering any of our questions yet. It's just going to help us to answer those questions. So the first question, part A, how many will there be after 10 hours? Now that's actually a pretty simple question. All we're doing is plugging 10 hours into our function. So we had 150 e to the, well, it'd be 0.2197, but if we multiply that by 10, we can basically just get to move the decimal place. So what is e to the 2.197, but then times 150? Again, use a calculator here. I'm not asking you to be able to figure out what this is off the top of your head. That is completely unreasonable. Use a calculator. Turns out it is 1,350 bacteria. There's a little bit of rounding that went on there, but it turns out that this is actually pretty exact. Now the next question, this is a little bit different. It's not just asking us to plug in a number. It's asking how long will it take for the population to double. So we're going to take our function, but we're going to ask what is the time t when the amount that we get out of this is equal to double the initial amount. Well, our initial amount, remember, was 150. So we're asking what t value gives you a y value of 300. Go ahead and write in our formula here. And we note that we basically just have another exponential equation to solve. This is actually very similar to when we solved for k initially. We just had some number equals some number e to a number times the variable that we're trying to solve for. And so we're going to follow pretty much the exact same steps that we had here. We'll solve for the exponential first. 300 divided by 150, of course, is just 2. In fact, that's where we got the 350, or the 300 from. It was just 2 times 150. So that shouldn't be surprising. In fact, you can kind of note from here that it didn't really matter that we started at 150. If we're saying that we wanted to find out how long it took to double, it was just whatever we had here times 2, and when we divided by whatever we had in front of the e, we just end up with 2 either way. This will become important a little bit later, that the initial amount here didn't really matter when we were talking about how much time does it take to double things. Of course, now we go ahead and turn this into a logarithm. So the stuff that's inside is now outside. The stuff that was outside is now inside. Go ahead and divide by essentially my k that was in front. We have the ln of 2 over this amount. And of course, we use a calculator to find out. We had 3.155, and this is in hours. Remember, our t here was given originally in hours. We had 5 hours here. So it'd take a little over 3 hours for this population of bacteria to double in size. Okay, part C. Does the answer to part B depend on the starting time? Well, we kind of actually mentioned that. I told you when we were going through this that the 150 just kind of got rid of itself because we were asking how much time does it take to double in size. We essentially put 2 times our c value on this side. Essentially, it turns into, depending on what c value we have there, we have e to the same kt, and we wanted to see when does that equal 2c. The c just drops out immediately. And we can just go ahead and solve the way we did here, and we get a formula. We get kt is going to equal the natural logarithm of 2. Or in other words, that t is the natural logarithm of 2 divided by k. This is a formula that essentially tells us that in any exponential growth problem, which is what we just started right here, in any exponential growth problem, we can derive a time t that it takes for this model to double the amount. It's frequently called the doubling time. And it's frequently given instead of just giving you the k value. A lot of these problems will give you something like, they'll give you another point on the graph that you need to use to solve for k, or they'll give you the doubling time. And the doubling time, you can essentially derive the k pretty quickly. You can solve this a different way and say that k is equal to natural logarithm of 2 over t. If they give you the doubling time, you take the natural logarithm of 2, divide by t, and it gives you the k value. So that's a frequently given way of approaching this. Now note, this only works for exponential growth, because exponential growth is the one that increases. We're not going to get double the amount we started with unless we increase. When it comes to exponential decay, we have to decrease instead, and so there we actually talk about what happens when we get to half the initial amount. That's frequently called the half-life. Basically, how long does it take for our model to equal half its starting amount? We can go ahead and solve this pretty much the same way. The c's immediately cancel each other out here as well. And that means that we're going to get kt is equal to the natural logarithm of 1/2. But because we have our properties of logarithms, natural logarithm of 1/2 is actually negative the natural logarithm of 2. So you can say here that the half-life is negative ln 2 over k. And note, this is actually pretty similar to what we had in the previous one. It's the same form, except we have a negative now. But keep in mind, the half-life is when k is, or the exponential decay is when the k is negative. So actually, this number here, the negative ln 2 over k, is a positive number in this case. But again, this is frequently given as a way of giving you the k value without just flat out giving it to you. For instance, what a lot of people probably think of when they hear the term half-life is radioactivity, because it follows an exponential decay model. So we're going to solve a problem that's similar to that uses this idea. We're going to talk about carbon-14. Carbon-14 dating assumes that the carbon dioxide in the Earth today has the same radioactive content as it did centuries ago. If this is true, then the amount of carbon-14 absorbed by a tree that grew 7 centuries ago should be the same as the amount of carbon-14 absorbed by a similar tree today. Basically, carbon-14 is radioactive, so that means it decays into a different element later on. And so if we can measure how much carbon-14 there is in something, then that means that we can determine how long it's been since that thing was alive. This works for living things. It doesn't work for other stuff. Or at least works for things that used to be alive in some form or fashion. So stuff that's made out of wood can be carbon dated. A piece of ancient charcoal contains, because charcoal is just burnt wood, contains only 15% as much radioactive carbon as a piece of modern charcoal. How long ago was the tree burned to make the ancient charcoal? And it gives us a half-life of carbon-14. This basically will allow us to get the k value for our model. Essentially, our model here is going to be y is equal to c e to the kt. Of course, the c here is not really given to us. They don't tell us exactly what amount of carbon-14 there was initially. But since we're working in terms of percentages of the initial amount, that won't really matter. But we do need to find out what k is. And we're going to go ahead and use this formula. Now, in the other form, so instead of solving for t here, we'd solve for k. K is equal to negative ln 2 over t, where t is our half-life. So if t is 5,715, that means our k in this case, we have to divide the natural logarithm of 2 by that amount and put a minus sign. And we end up with a negative 0.0001213. So half-life of 5,000 years is actually pretty big. It means we have a very small k, or at least small in a negative fashion. All right, so we're asking, when is the y equal to 15% of the initial amount? Well, 15% of c is 0.15 times c. And we have this k value times t. So what value of t makes this true? Of course, like I said before, c's don't really matter here. So we end up taking the natural logarithm of both sides. We get that negative 0.001213 t is equal to the natural logarithm of 0.15. If we just divide by this over here, and then just use a calculator, of course, get a value of 15,640. Of course, this is in years, because that's how we calculated our half-life before. And this kind of should make some sort of sense. So keep in mind that the half-life means that after 5.7 thousand years, we have half of what we had originally. So when you can say that we originally had c. Maybe make a table of this. So at time 0, we had we had c. This would be our y. After 5,715 years, we have half of c. After double that, basically after another 5,715 years, we're at 11,430 years. We're half of what we had here. We're not going down to 1/3. We're going to 1/4. Every time we go over a time span of 5,715 years, we have half of what we started at that time span at. So started here, 1/2 of c. After that amount of time, we're at half of what we started with. The 1/2 of c needs another 1/2. If we go another stage and add on another 5,715 years, we're now at 17,145 years, but now we're down to an eighth. An eighth is basically 12.5%. So you can see that we kind of shot past the 15% that they had here, and our time is a little bit further than what we had here. So it makes sense that if we don't quite go 17,000 years, we don't quite get down to an eighth of c. But finding out exactly the amount requires kind of working with this exponential. We can't. It's kind of awkward to try to figure it out just straight up by having things as we go. But at least it's consistent with that idea. We can also apply this to the world of investment. So here we talk about a rule about how long it takes things to the amount of an investment to double its value, where we were told to derive some rule of 70. Basically saying that after 70 years, things should be doubled. Or, well, not 70 years. 70 divided by the annual interest rate. Why is this value true? Where did the 70 come from? Well, we're following a continuously compounding interest model. We have the A is equal to PE to the RT. We're using R and P instead of C and K, but that's okay. That's not too big of a problem. It's just what variables do we use? This is an exponential growth model, and we can talk about its doubling time. Basically, when is A equal to 2 times the principal, P? Well, we get down to our formula that R times T is the natural logarithm of 2. Remember, that's from our doubling formula. Or we can go ahead and write that as the doubling time T is ln of 2 over R. What is ln of 2? Go ahead and use a calculator for that. It turns out the ln of 2 is 0.693 and so on over R. Well, what we're going to do here is approximate this, because this is kind of an annoying number to work with. We'll approximate that as 0.7. Now, that's not the formula they got here, but notice that they specifically said that they want it to be entered as a percent. Here, r is not being treated as a percent. In order to make it a percentage, we need to multiply the r by 100. And to not change our doubling time formula, that means we need to multiply the top and bottom by 100. So we'll get that t is 100 times 0.7, or 70, over r, where r is now as a percentage. So this is as it is. This is as a percentage. So we get this rule of 7 that they refer to. Now, it is a slight approximation, but then again, most of the times we don't really use the continuous compound model. It's just a nice way of actually working with it, rather than having to, say, work with. If you remember back to when we did compound interest before, working with a time span or a number of compoundings per year of 365, a daily compounding, was kind of annoying. Here we actually get to just work with e, and it becomes a little easier to work with. So we're already doing a little bit of an approximation to work with e in the first place. If we do a little bit more approximating after that, we can get a formula that's easy enough to work with. In 38, we're going to go ahead and apply this, but it's really easy to apply it, which is why we have this formula in the first place. If the rate is 10%, we just plug in 10 for r. Notice that because we're dealing with percentages for r in here, then we just drop the percentage sign. 70 divided by 10 is 7. Of course, this is in years. So it's saying that if you have an interest rate of 10%, then you should expect your investment to double in size in about 7 years. On the other hand, if the r is 7, or 7%, then we expect to take 10 years. Pretty simple formula. But it's the simpler formulas are probably the ones that are the most enticing. Alright, so just trying to give you an idea of how to work with these exponential models. They're all these problems are basically kind of the same way. We start with that model of y equals c e to the kt. We might have to solve for k. They might give us k in a half-life or doubling time fashion, instead of just giving you a point on the curve, things like that. And this is how you would handle these kind of situations. Now, there are a couple other models that we could use for things, so I'm going to have another video where we talk about a couple other types of problems that are related to exponential growth and decay, but not quite the same. So I'll see you there in the next video.